And we are live on the internet. All right, so welcome y'all to Calculus. My name is Gary Parker. I'll be teaching the class this term. Just a few things about the setup for the course. Pete used Zoom. I don't really like Zoom. I like Google Hangouts because it sends all my videos straight to YouTube after, and they're easier to manage there. So if you ever can't come to class, you just send me a Google address and then you can join a live Hangout. To view them, you just go to my YouTube playlist, which is listed somewhere here. So let's see. Introduction, read the syllabus if you haven't already. There's a cute video here by an old guy that teaches calculus that I thought was a nice introduction. It's more for Calc 1, but he introduces Calc 2 and Calc 1 at the same time. And then I put 2 videos up here for what I covered yesterday, and I'll review a little bit of that today. It's about half an hour, 38 minutes altogether. Somehow my computer shut down when I was trying to finish up this one, so there's the additional 8 minutes here. So check that out soon. Everything should be accessible from this homepage here, modules. There's a calendar of what I hope to cover each day. Given snow days, we'll cover, I'll make up videos anytime we have a snow day for you so that we don't miss stuff. But it's likely to put us behind on this calendar, but we've got a few days at the end here in which we get some slack. So days may shift a little bit, but I'm hoping for to finish chapter 5 and have the first exam in the end of the 3rd week. We'll see. It's a good chance we can pull that off. Modules. Resources, I like collecting things, especially about math. So here are some math things online. So for example, anybody here have the printed book? Yeah, okay. I love getting stuff from a printed book, so use that. Here's a PDF available of the book. Sometimes those ebooks are annoying, and so this is just one big file with the whole book in it. So feel free to take a look at that. I have some other calculus courses I've been messing around with online, and there's videos you can go play with here. And then some other books if you ever want additional examples. When I was a student, I always liked to see as many examples as possible when I was trying to figure something out, and I almost always looked in other books. So none of this stuff in the resources section is required. Under other stuff here, that's my YouTube playlist. So every time I do a recording, it goes into that list. And so you can look things up by date or by topic. And right now there's only 2 videos, but there'll be more as we move on. And 2 of my favorite pieces of math software that are kind of sort of free are GeoGebra and Wolfram Alpha. And so if you haven't used either of those, I'm going to try to get you to use those this term. So we'll play with GeoGebra for sure today, maybe Wolfram Alpha. Anybody used Wolfram Alpha before? I have one nod. Everyone else is like, oh, what are you talking about? No. Oh, somebody's online. Who is that?
It's me, Michael.
Me, Michael. Hi, Michael. Welcome. It's good to hear you.
Yes.
You can see the screen okay, and
yeah, everything seems fine. I don't know how my gain levels are, so I might be a little bit loud. So
okay. All right. I am going to adjust this. Let's see. How do I do that? So that when you talk, it doesn't take over the screen. Right here, no, right there, present to everyone. Okay, there we go. All right, so talk when you need to, ask questions. All right, so let's see, other stuff. So the modules, there we go. You should, if you were in the course last term, just be able to go to all assignments and grab an assignment and go with it. With the way the grade sync works, I have to grab grades periodically. They don't automatically update as you do stuff. I don't know if you noticed that last term. Yeah. So what that means is there's assignments, and those assignments get grades from MyMathLab, but only when I tell MyMathLab to send them over. So although these are listed in the assignments, clicking on them does us no good. They don't lead anywhere. So you probably learned that last term too. So the only way to get to assignments is either from MyLab's Mastering, and then there's a link over here for you. You don't get those links, but you get these 2 to get to the assignments, or I put another link in modules. And then the multimedia library can get you to the book and videos and other stuff. And then this is just a link to the main site. And then I'll also post in here what sections I plan to cover each week. It's kind of redundant because I already have the calendar, but I don't want anyone to forget where we are in the course. So I put it in multiple places. Let's do some math. So we are playing with area problems. So just a quick snapshot of the video from yesterday. There's a connection between rates and areas, which is kind of remarkable. So the simple example I used yesterday in the video was if a car was moving along at a constant rate of, say, 30 miles per hour, and then we track that car over time, 1 hour, 2 hour, 3 hours down the road, we can turn this graph into a graph of distance versus time.
Hello.
Okay. Hello, who do we got there? Darren.
How to get in? I found the way in.
Darren, can you see the screen okay?
Yes.
Okay.
Did I miss anything important that wasn't covered in there?
Nope, not yet. We've just been talking about what's in Canvas. We just started doing math this very second.
Okay, sweet. I joined the perfect time then.
Okay, so consider after 1 hour, right? We'll have 30 miles per 1 hour. And we know that distance equals rate times time. So taking that rate times the 1 hour, the hours cancel, leaving us after 1 hour a distance of 30 miles. So 1 hour later, we have a distance of 30. So that puts us right there. All right, who else do we got there? That looks like Devin. Is that you?
Yeah, hey, Mr. Parker, how are you?
Okay, good. All right, so you might need to mute your mic when you're not talking, otherwise we're gonna get some feedback.
Okay, yeah, I see it. I'll do that.
Okay, thanks. Okay, so, and pretty simple process as we continue that, we multiply by 2 hours, then 2 hours later, we have covered 60 miles and so on down the road. Now, the cool thing about that is consider this rectangle right here on this graph. The horizontal axis is measured in hours, so we have a base for this rectangle of 1 hour. The vertical axis is a rate measured in miles per hour. So the height of this rectangle is 30 miles per hour. Multiplying those two together, like I did here, leads to 30 miles, which also happens to be the area of that rectangle. So this was discovered a few hundred years ago by guys named Newton and Leibniz. And that's when calculus has actually been around much longer than those guys. But it was this connection between rates, slope of a line, rates of change, and areas. So people were studying area problems, people were studying these rate problems, and then all of a sudden a few of them realized, like, oh my God, they're two different directions of the same problem. So that's what we're going to explore over the next 2 days, how the rates and the areas are related. That will culminate in section 3, where we look at what's called the fundamental theorem of calculus, which is the official connection. Oh my gosh, it's snowing again. All right, thank goodness for the internet to get connected, huh? All right, so that was like the essence of the video from the other day. I did a couple of other examples, and then the other examples I did with more complicated curves. I'm going to just continue over the next couple of days. But please go back and watch that video if you haven't already. All right, so we've got a remarkable connection between rate, slope of a line, and when we graph that rate as its own function and the areas under that particular graph. Okay, so let's try something simpler. Let's take a look at the function y equals x. Okay. And graphing that is pretty straightforward. We have the 0.00 and the 0.11 and the 0.22. So we get a line that looks pretty much like that. And so what we're going to take a look at is some approximations. So we'll just do a simple example first, then we'll do something more complicated. When we're approximating curves, and let's put a more complicated one underneath for comparison, like y equals x squared. Here we have 0, 0, 1, 1, and 2, 4, right? We get this beautiful curve called a parabola or parabola, depending on where you grew up. Everybody that has a dish TV loves this shape because that's the basis for it. It's not too bad to find the area under this curve over different intervals, because they're just either triangles. We know how to find the area of a triangle, or in this case, a trapezoid. There's an easy formula for the area of a trapezoid. Where things get more interesting is when we try to find the area where part of it is curved, right? Off the top of your head, do you remember any area formulas that have to do with curved shapes?
Circles.
Circles, yeah, everyone knows circles, right? Pi r squared. But we haven't in our life seen many formulas for areas related to a parabola or some other curved shape, right? Can you think of that? Anyone remember that off the top of their head, seen that before? Look up area formulas. Hey, there's the area of a parabola. No, blank. No, I've never seen that before. Okay, so that's part of what we're going to try and develop here. We're going to try to find a way, given this curved boundary there, to discover what the area is inside there. Okay, and the previous example says, well, there's a connection between rates and areas, and we're going to exploit that connection eventually, but we got to warm up to it first. So we could have no problem finding this particular area right here, right? So if the area I've shaded here, if we went from 1 to 3, the first area is a triangle. Area of a triangle is 1/2 base times height. This triangle is 1 by 1. Base times height is 1. So the first piece of area is 1/2. And then we would add on to that. Let's see if we break that into pieces. Let's get a highlighter. We've got a 1 by 1 rectangle right there, right? Plus we have a similar triangle to the one we just did right there. So altogether, what's that next bunch of area add up to? 1.5, yeah, or 3/2 if you like improper fractions. Then we continue that into the next one and we see, well, we've got another square here and another square there and another triangle there. So we're going to add on another 2.5 there, which is 5/2. You see a pattern to the numerators there? Like, could we continue this pattern? Yeah, so let's talk about patterns for a minute and then we'll come back to this sucker. All right, so we just generated a pattern. We had 1/2 and then we had 3/2. And then we had 5/2. What do you think is going to be next according to this pattern we're starting to develop? 7/2 seems pretty natural, right? 7/2. Now in math, we've got this weird fixation on formulas, right? Just give me the formula, please. How many people think that in class? The teacher's going on and on about something. Just please give me the formula. So I would like to know, like, is there a formula for these guys? So if somebody says, okay, I need 100 of them, what's the 100th one going to look like? Okay, so let's think about that. Usually when we're looking for a formula, we have to plug something in to get something out, right? So I could say I have a first, oops, wrong button. I have a first term and I have a second term and I have a third term and I have a fourth term. Right, term is a piece of a sum. Think back to arithmetic. So these are the terms. And then these guys here are my what are called partial sums. So I guess it comes down to I need a formula to generate odd numbers, don't I? Well, even numbers are easy. How do you generate an even number? What's the 10th even whole number? 20? Yeah, right? 2 is the first one, 4 is the second one, 6 is the third one, 3 times 2 is 6. Okay, so even numbers are pretty easy. How do you get from an even number to an odd number with arithmetic? Add 1 or subtract 1, yeah. Before every even number is an odd number and after every even number is an odd number. So our formula, I think, is either 2n plus 1 for the numerator or it's 2n minus 1. All right, let's see which one works. Well, we could test it for 4. If I plug in 4, I want 7. The first one says 2 times 4 is 8 plus 1 is 9. Oops, that's too big. Second one says 2 times 4 is 8 minus 1 is 7. Bingo, I found it. So now I have a formula. I can get any term I want with an equation, which is kind of neat. So in this case, each term here is a 2n minus 1, and then we cut it in half, divide by 2. Okay, now we have ways to summarize sums, and that is with this letter right here. Have you seen that before? That is the capital Greek sigma. And it's very famous because of Microsoft Excel. They have a button with that on it, which means add stuff up. It's the sum button, right? So now we have this symbol for calculus. So it means add stuff up. N is usually an endpoint in what we're doing, okay? So when you add things up, you need to say where to start. Usually that goes on the bottom. Like start with 1. And then where to end. Like up here, I ended at a 4th term. So what this says is starting with 1, go up to 4, okay? To do the counting from 1 to 4, we need what's called an index. I like the letter I for an index. The book likes the letter K. That's okay. Sometimes I'll use I, sometimes I'll use K, sometimes J. And the things that we're adding have to look like that. Now, N is, again, usually an endpoint. So I'm not going to put an, I have an I here instead of an N. So instead, my formula should look like this, 2 times I minus 1. Because I is my counter. Right? An index is a counter. It's your position somewhere. So I want to add up these things that look like that. And so just double check that. If I plug in the first value of the index, 1, then I get 2 times 1 is 2, minus 1 is 1 half. Add. N jumps, jumps up to the next number, 2. 2 times 2 is 4, minus 1 is 3. And then we just keep going. I then jumps to the next index, 3. 3 times 2 is 6, minus 1 is 5. And finally, we hit our last value of our index, which we know leads to 7/2. So we're often going to use summation notation to make these sums shorter in appearance. So this means the same thing as that. We happen to have a common denominator. That makes it nice. What do we get? 7 and 3 is 10, 15. This adds up to 16/2 or 8 would be the area we just calculated. And sometimes we're going to need that summation notation, because what if we had to do like 100 of these? Do you really want to write out all 100 fractions? Answer is no, we don't. We're going to use technology to do that for us, but we need shorthand notation to communicate that, okay? All right, so I just want to go over, I'm going to come back to this sucker in a few minutes, but I just want to exploit summation notation a little bit more. So I'm going to use a different index. Suppose I wanted to find the sum, as some counter I goes from 1 to, let's go up to 10 of I. I want to add up the index. So first I gets to be 1, and then I gets to be 2, and then 3, and then 4. This is getting kind of boring. Good thing I didn't go higher than 10. Oh, and I ran out of room. Let's move all that over. And then we can add 10. All right. Did I get anyone else in there yet? Not yet. Got the 3 of you still hanging out. Good to see you still. All right. And that's not too bad. We could all perform that. But I want to show you a trick. So adding 1 and then 2 seems like slow progress. Wouldn't it be more productive to start at 10? Right? Because 10 plus 9 is 19. That's way bigger than 1 plus 2, which is 3. So don't you think it'd be more efficient to add the sum in this direction? Or am I being foolish?
I've got another idea that you could do.
Oh, what is it? Who's that?
Add 10, then you plus 9 plus 1, then plus 8 plus 2 plus 7 plus 3.
Oh, shit,
So
look at that. Darren sees a pattern that if we pair numbers together like 9 and 1, that makes a 10. 8 and 2, compatible, makes a 10. 7 and 3 is another 10. 6 and 4 is another 10. Then we get that 5 there. So he found a shortcut to say this is 10, 20, 30, 40, 55. Okay.
Yep.
I noticed another pattern after I wrote these backwards. Check this out. When I look down this way, what's 10 and 1? Well, it's 11. What's 9 and 2? That's 11. There's a whole bunch of 11s here. How many 11s do I have? I have 10 of them, right? There's 10 numbers here. Yeah, so I'm not pairing them like Darren is. I'm doing a slightly different approach. There are 10 across there, right? So if I add these together coming down, I'm going to get 10 11s. Now, unfortunately, what I just did is I doubled my sum when I did that, didn't I? Yeah. So twice the sum is equal to that. Okay, so can't I solve for the sum then by doing what, division by 2? 10 times 11 over 2. 110, cut it in half and I get 55. And it turns out this trick, either by pairing things like Darren did, or by writing the sum in opposite order and adding the two equations together, it works for any list of numbers whose terms are the same distance apart. 1, 2, 3, 4, 5. Are those all 1 apart? Okay, so my claim is that would also work for 1, 3, 5, 7, 9, 11, odd numbers. Okay, they'll always work like that. So I'm just gonna take this another step further. What if instead somebody said, all right, oops, that's a messed up sigma. I got too excited. Try again, use black. What if instead, let's use K, let's go from 1 to N. Oh wait, what is N? What's the endpoint? Okay, is it 10? No. Is it 100? Maybe. It's just some number out there. And I'm gonna add the K's up, like I did earlier. But this time I'm not telling you where to stop, sort of. 1 plus 2 plus 3, dot, dot, dot means continue this pattern, and then end at whatever N is. Okay, here's a trick question. What number is right before N? Oh man, you guys are wicked fast. N minus 1, okay. So really I could say there's an N minus 1, and then I get my N. And what would be before N minus 1? Ah, you guys are way too good. Okay, N minus 2. So now I'm going to try my trick I used earlier. I'm going to write them in reverse. So I'm going to say, okay, there's an N, and then there's an N minus 1. Then, just to give the 3 something to do, there would be an N minus 2, yada, yada, yada. And then I'm going to end with a 2 plus 1. Does a pattern emerge when I add down? Yeah, there's a whole bunch of n plus 1s. Yeah, so that's kind of cool. So when I add those guys together, well, I get an n plus 1. And then when I add those guys together, well, I get another n plus 1. How many n plus 1s, plus 1s did we just generate? Well, how many numbers were in my list up here?
N.
N of them. So a shorthand for the red stuff here is I have n plus 1s, right? Repeated addition is multiplication. Catch, is that the sum I want? It's twice the sum, right? Because I took this sum and I looked at it that way. So altogether, all this red stuff is twice my sum. I'm just going to call it S. So that means S must be equal to that product over 2. Now I've got a shortcut for any n you give me, whether it's 100 or 1,000. I don't have to list them all. I just plug it into that sucker and I get an answer. Isn't that wicked cool? This is so cool. Peter's writing it down. That's got to be good. Now you might ask yourself, well, if there's patterns for adding up just the index, doesn't that mean there's probably patterns for when we add up other types of stuff? And the answer is yes. Now here's the trick. They're all different. Right? So check this one out. This one's really cute. How are we doing on time? Oh, we got plenty of time. Let's suppose I was going to add up odd numbers. We discovered a representation for odd numbers earlier that said they look like a 2n minus 1 or a 2n plus 1. Okay. Now, n is usually my endpoint, so I shouldn't put that inside my summation. So I should use something like I or a k. Anybody got a favorite, I or k? K. Peter says k. Okay, so we're going to throw a k there. So that means I'm going to start counting at k. If I want my first odd number to be 1, then I should start with k equals 1. And then let's go up to, let's make this a really easy one. Let's just add the first 2 odd numbers. Right? We'll get brave in a minute, and then after that, we'll add the first 3 odd numbers. Now, depending on the teacher you have, some people are sticklers about parentheses, others aren't. Like you may have had teachers that wrote the sign of X like that, and others that wrote it like that. Okay. I'm usually pretty careful with parentheses, so often if I have a complicated sum and like this, I would usually put it in parentheses. Sometimes I get excited and forget, but we always want to know, because sometimes there'll be more stuff going on, what's being added and what's outside of the control of the sum. Oh shit, that was an eraser. Sorry. The sum. Okay. So the first one says plug in 1, and then we get 2 times 1 is 2, minus 1 is 1, and then the second odd number is going to be 3. 1 plus 3 is 4. Okay. This one says just throw one more term on the end, right? We just jumped up to 3. So I'm going to have 1 plus 3 plus 6 minus 1 is 5, right? It's generating odd numbers. 1 plus 3 plus 5 is 9. Okay. Some k from 1 to, ooh, no, let's do something more complicated. No, we'll stick with this one. 1, let's go up to 4. I'm adding odd numbers, 2k minus 1. So that means I'll have 1 plus 3 plus 5 plus 7, which adds up to 16. Is there anything interesting about the numbers I'm getting, my partial sums? They're perfect squares. There's something even more special about these perfect squares. How many odd numbers did I add up in the first part? 2. How many odd numbers did I add up in the second part? How many odd numbers did I add up in the fourth one? So anybody want to make a prediction? What will be the sum as k goes from 1 to 10? What's the sum of the first 10 odd numbers? It's going to be 100. Oh my gosh. 1 plus 3 plus 5 plus 7. Let's see, the 10th one is going to be 19. So if we add odd numbers, 1 through 19 is going to add to 100. That's the conclusion we're coming here. Now, we didn't prove this. This is just an observation. And this happens a lot in math. People play around. They're like, ooh, that looks like a pattern. And they say, okay, I think this is where the pattern leads. But then eventually they have to have some concrete proof that that works. So here's some concrete proof that that works. So I want to sum. Let's see, we're using K. Sorry, I started writing an I, old habits. K goes from 1 to N. And, oops, forgot my sum and. Yeah, so the whole thing is called the sum. The thing you're adding is called the sum end. And we are adding things that look like 2K minus 1. And let's see, that means we're going to have 1 plus 3 plus 5, yada, 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 all the way up to, what's the last odd number we're going to add? 2n minus 1, correct. 2n minus 1 is the last one I add. Ready for another trick question? What odd number is right before 2n minus 1?
2n minus 1 minus 1.
2n minus 1 minus 1. Well, that would be 2n minus 2, which would be an even number. 2n minus 3 is the one right before this one. Yeah, because we're jumping by 2s, right? Aren't these guys 2 apart? Yeah. So I could say this is really a 2n minus 3, and I could say there's one more out here. That's a 2n minus 1. And let's pull that trick we just did a minute ago where we reverse it. Okay. So if I reverse it, then I'm going to say this is a 2n minus 1 plus 2n minus 3 plus dot, dot, dot. And then down in the end here is going to be a 3 plus a 1. Is there a pattern emerging when I add things coming down? Well, what's 2n minus 1 plus 1? 2n. Okay, so there's a 2n. And then the next is going to be a 2n. And let's see, what would be right before 2n minus 3 as an odd number? It would have to be 2n minus 5. It's got to be, yeah. So we're going to get up a whole bunch of 2n's. Okay, another trick question. How many do I have? N of them, yeah. I started at 1 and I went up to n. There's n of them here. So now I have 2n times n, but again, that's twice my sum. Cleaning that up, s has to be 2n times n over 2, which turns out to be n squared, right? N times n. Yeah, the 2's divide out. N times n is n squared. It's the square of the number of odd numbers. We've proved it, without a doubt. As long as you start at 1 and continue by every odd number in order. Wicked cool. So, is there a formula for anything you try to add up? Probably. Sometimes it's really hard to find. Okay, I'm going to omit the proofs of the following formulas. It turns out if we tried to add k equals 1 to n, the squares of the counters, so that would be 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to whatever we say to stop, n squared. Turns out there is a pattern. It's way harder to find than the ones we just did. I'm just going to give it to you. If you're dying to know how to prove this is true, then maybe Friday for fun we could do it. It turns out this is n times n plus 1 times 2n plus 1 all over 6. There's a couple of ways to prove it. If you searched online for sum of squares, you would find it if you can't wait till Friday. Sum as k goes from 1 to n of the cubes. 1 plus 8 plus 27 plus 64, I think. all the way up to whatever n we stop at, cubed. This one's crazy. N times n plus 1 over 2 squared. Some interesting patterns here. When we add whole numbers, numbers that are 1 apart, the formula had a square in it. When we add numbers that are squared, really I have an n times n here. We have a cube as the highest power in the closed formula here. And what's the highest power we end up with here? 4th power, yeah, because we're going to have an n times n inside, but that's squared 4th power. Yeah, so it turns out there are patterns going on here. There's no easy way to say, looking at these two, what the sum of the 4th powers is going to be, except that it'll have something to do with n to the 5th power. Okay, it's findable algebraically. It's just a pain in the butt. Right? Do you need to know it? No. This is more than enough for us to work with here. All right. So let's back up to another problem. We got 5 minutes. So I said I would come back to y equals x squared. And so let's just jump to a harder version of this problem. Let's say 1, 2, 3, 4. Let's see, 4 squared is 16. So on this axis, I'll graph by 4s. So 16, 12, 8, and 4. And so to graph this, I know that we have the point 0, 0, 1, 1 is going to be about there. 2, 4 lives about here. 3, 9 is about here-ish. 4, 16 is somewhere over there. And we get that beautiful parabola. I want to try and estimate the area of this guy on the interval from 0 to 4. Oops. Endpoints don't really matter, but I want that 4 to be included. And I want n equals 10 subintervals. All right, so we're going to set up an interval notation, a summation notation for this, and then we're going to add it up on a computer because it's easier. 10's not too bad, but, and I do a similar problem to this with 4 subintervals on that video. All right, so let's see. How big is my interval? How long is it? It's 4 units wide, right? So my total width of the interval is 4. So that's the width. And typically, we want all of our subintervals to be the same width. Do they have to be? Nope, don't have to be. So usually we take the width divided by the number of subintervals, and that would be 4 over 10, which simplifies to 2/5 if you like fractions. I like fractions. Or you could write 4/10, 0.4. This is what we call delta x, which you've probably seen before in Calc 1. And like in Calc 1, when you found instantaneous rates of change, you let that delta x get smaller and smaller and smaller, which means we want to have more and more and more subintervals. Okay. All right, so that's the width of each interval. Okay. So let's see. I'm going to be generating a bunch of rectangles. So let's just examine a couple of rectangles. So there's going to be a rectangle over here that's going to look something like that. What's the width of each rectangle going to be? If I have 4 to start with, I divide it by 10. Didn't we just discover that the width is 2/5 of each subinterval? Okay. So the area of a rectangle is always base times height. And my base in this case is my width over n, which is 2/5. Okay. To get the height of my rectangle, I have to pick an x value in that interval. We usually call those the x sub i's, to plug into my formula to get a height. Okay, so let's say I am at an interval of 3. then the x value on this side would be 3 2/5, right? Because every interval is that wide. And usually we do one of three things. We either pick the left side of the interval to get the height, or we pick the right side, or we pick the midpoint. Let's go with left side. So if I'm going with left-hand endpoints, then for this particular one, I would be plugging in 3. Now I need to find a pattern for this if I'm going to use this subinterval notation. So I would say then my height here is going to be 3 squared, right? That's just this rectangle right here. How many rectangles do I have? I have 10 of them. Okay, and we could figure out each one pretty straightforward. Let's do that on a new page. All right, so let's see. I'm using left-hand endpoints. And so on that interval from 0 to 4, what's the leftmost endpoint? 0. Yeah, so the first height is going to be, the base is always 2/5, and the first height is 0 squared. Then I slide over how much for the next interval? Another 2/5. So the next one is going to be a 2/5 for the base times the height. Well, the next x value over happens to be 2/5. But to get the height, I have to square that sucker, right? Then we jump over to the next one. How far over is the next one from 2/5? Another 2/5. 2 plus 2/5 is 4/5. So that means I'm going to have still my base of 2/5. My height, however, is going to be 4/5. And I'm going to keep moving on down the road. So just keep in mind here, this is my first rectangle. This is my second rectangle. That is my third rectangle. What's the fourth rectangle going to look like? 2/5 times 6 over 5, and that needs to be squared. And we just keep on trucking. There's 4 of them. We got 6 more to go. Okay. What if there were 100 more to go? We don't want to write them down. We want to discover a pattern. What's changing here each time? The numerator. Ooh, ow. So we need to find a pattern between the rectangle I'm at, the first, the second, the third, and so on, and the number that's changing in here. Okay, what do we know first? They're even numbers, right? Okay, so we know that down the road, there's going to be some 2i numerator. Okay, let's see, if I plug in 1 times 2 is 2. Do I want the first one to be a 2? No. The second one, if I plug in 2, I get 2 times 2 is 4. Do I want it to be a 4? No, I'm off a step. Okay, I'm off a step. Trick here, let I be I minus 1 in parentheses. That'll shift it back for us. So now, for example, let's try 3. If I plug 3 here, 3 minus 1 is 2. 2 times 2 is 4. Ah, I got where I wanted to be. Okay. Could I have written 2 times parentheses I minus 1 differently? Yeah, I could have wrote it as 2i minus 2 without the parentheses. So there's usually different ways to get to it. But I now have the numerator. That has to be divided by 5, and it has a width of 2/5. Okay. And so each problem is unique, trying to come up with a formula. So here's what I've discovered. In summation notation, I have I going from 1 to 10. The base is 2/5, we'll be out in just a minute. And the height is 2 times I minus 1 over 5. Why would I need to know that? Well, I could plug this into a computer program that would then just add those up for me. What kind of computer program? Well, TI 80-somethings have this built into them. You could do it there. Some scientific calculators have a summation notation, or you just whip out some program like GeoGebra or Spreadsheet, Excel, Google Sheets. They all can do this. Oop, I'm out of time. So I will have to get to that later because we are out of time. Just for fun, my next step would be to jump into GeoGebra, because GeoGebra can do sums and it can do rectangles of functions areas. So really slick. And I think I demonstrated that in the video yesterday. Did I? Does that sound familiar? I did. Okay. Yeah. So there's a demonstration in the video of using GeoGebra. Highly recommend you check it out. So we reviewed a little bit of yesterday. If you haven't seen the video, check it out. It's 38 minutes long from yesterday. We have covered material in section 5.1 and 5.2. According to the calendar, we're going to stay on 5.2 tomorrow, so it's more of this stuff, which is pretty close to what's in 5.1, and 5.3 takes it one step further, which we might get to Thursday. So we might stay on schedule, we'll see, over the next couple of days. So give the homework a shot, go in there and play around. Please read the book. They explain things using slightly different words and examples than me. It's a valuable resource that you paid a lot of money for, so I highly recommend you check it out. And email me if you have any questions. Otherwise, I will see you either in class or online tomorrow. Have a wonderful day. All right, anybody online have any questions before I sign out?
Nope.
1 second. You guys are good?
And oh, this will be on YouTube, so I can see the first 10 minutes that I missed.
Yep.
Okay.
It'll be there.
See you tomorrow.
All right. Okay, bye-bye. All right, stop.